if the Turan hypothesis is true, that implies, by Bohr's equivalence theorem, that summation lambda n over n to the s, n less than or equal to x, is, maybe I should put, since I put n, okay. For n less than or equal to x is non-zero for all x greater than or equal to x naught and no other x naught. I'll replace by something else. Because the set of values are the same. But the limit, as sigma tends to infinity, of summation 1 over, lambda n over n to the s, n less than or equal to x, is 1. Remember, it's only the first term that dominates. When your real part sigma goes to infinity, the next one is 2 to the sigma, 3 to the sigma, 4 to the sigma. They have no consequence. So all Dirichlet series approach f of naught, the first coefficient, or a naught. So this approaches 1. So now, this is only on the, I can put s here. Okay. So now, observe the following. Note that summation lambda n over n to the sigma, n less than or equal to x, is a real value. Non-zero. And approaches 1 as sigma goes to infinity. So what does that mean? That implies that summation lambda n over n to the sigma, n less than or equal to x, is always greater than or equal to 0. Because if it is less than 0 at some point, and it is approaching 1, as you then proceed to the right, somewhere it is going to cross the axis. Always why it is true, I've always extolled the use of complex variable theory, but real variable theory has some topological usefulness. So that implies that this is greater than or equal to 0, which implies that by taking limit sigma tends to 1 plus summation lambda n over n, n less than or equal to x, which we will call as c of x, is greater than or equal to 0 for all x sufficiently large. So what we're saying is the partial sums of this series turn out to be non-negative. So now we go to 6. Now, this is an integral with this thing being non-negative. Landau's theorem is about Dirichlet series with non-negative coefficients. Non-negative means eventually non-negative coefficients. But every Dirichlet series can be written as an integral with a d something integrator. So we can formulate a Landau theorem for integrals, just as we have a Landau theorem for Dirichlet series. We can formulate a Landau theorem for integrals. It will be exactly the same. So when you have an integral version of Landau's theorem, if this is non-negative eventually, and you want to analytically continue, your obstacle will first hit in the real axis. That's what Landau's theorem says. Okay. We now apply the integral analog of Landau's theorem to 6 with C of u greater than or equal to 0 for all u greater than or equal to u naught. So the first obstacle to analytic continuation is on the real axis. Now look at the left-hand side. Look at the left-hand side of 6. That's an analytic function, paramorphic. Where do you get the first obstacle to this as you burrow through the real axis? Only when zeta has a 0. But zeta has no 0 on the real axis. On the real axis. So zeta has zeros on the half line, but zeta has no zeros here. We proved that some time ago. Therefore, as far as the denominator is concerned, all right, s minus 1 zeta s is not a trouble. The pole and the 0 match. But I can then continue to the left, all right, until this gives me a pole. That gives me a pole at half. Okay. So the left hand, look at the left hand side of 6. This is analytic up to s equal to 1/2 plus epsilon on the real axis. So by Landau's theorem, zeta 2s divided by s minus 1 zeta s is analytic in the half plane. Sigma greater than half. This is beautiful. See, what is happening is we are representing this in terms of like a non-negative Dirichlet series, like a non-negative integral analog of a Dirichlet series, and applying Landau's theorem. So if this is analytic in sigma greater than half, then that means the denominator is non-zero, and that's the Riemann hypothesis. So this stunned the world that Turand found. The proof is not very difficult, right? But it's a beautiful example that this is true. Now, so what happens? This is false. But not to sort of start mourning. 1958, Hazelgrove, by machine computation, showed that C of x oscillates in sign infinitely up. So the Turand hypothesis is false. But not to worry, Turand modified his theorem. So we'll call modified Turand theorem. And that still has not been proved to be false. Okay, but this is all stronger than the Riemann hypothesis. So modified Turand theorem. What is modified Turand theorem? If C of x is, so this oscillates in sign, right? So what Turand says is, if it doesn't go to the left too much, then the Riemann hypothesis still goes. So what does it mean by saying it doesn't go to the left too much? So if C of x is greater than some constant log to whatever power you like over square root of x for some C at alpha, okay? Then Riemann hypothesis follows. So let's prove this. Now this has not been disproved because this involves some C and some alpha. And so initially there might be a little bit of left, but in an asymptotic sense, it's like this, right? So you can't just do this by machine computation. You got to actually do it by actual theoretical considerations. So the proof goes as follows. 8. Now clearly, 8 implies that C of x is greater than 1 over x to the power half minus epsilon. You agree? Minus. Because log is absorbed in x to the epsilon. All right? So now define a of x equal to C of x plus 1 over x to the half minus epsilon. And what can you say about a of x? Then a of x is positive for all x greater than x naught. So instead of C of x in this integral, we'll deal with a of x. That's your non-negative integral analog of the Dirichlet series. Okay. Now observe that the integral from 1 to infinity a of x over x to the a of x or a of u, it doesn't matter, over x to the s dx, the integral from 1 to infinity C of x dx over x to the s plus the integral of 1 over x to the power half plus epsilon. So that means it is s plus half minus epsilon dx of 1 to infinity. All this is in sigma greater than 1. And now this gives me, the first part gives me zeta 2s over s, zeta 2s over s zeta s, s minus 1 zeta s, as I had before. That's the first part. The second part gives me, I can evaluate this exactly using antiderivatives. The second part gives me 1 over s minus half minus epsilon. Now, I can apply the theorem to this. The only difference, or the beauty about this is the half. See, previously, so again, apply Landau's principle, non-negative. So as I burrow through on the left-hand side, the first obstacle must be only on the real axis. This has no obstacle on the real axis till I hit half. This has an obstacle on the real axis at half plus epsilon, but epsilon greater than 0 is arbitrary. So this is by Landau's theorem, analytic in sigma greater than half plus epsilon. But epsilon is arbitrary. Therefore, Riemann hypothesis follows. Now this has not been disproved. But this is a statement not about the truncations of the Riemann zeta function, but a statement about the oscillation of the series lambda n over n. So it's a different modification. So Turan's theorem is modified. So the truncated Riemann zeta function is thrown out the window. So Montgomery told me a joke, and I will tell you when this joke comes in, because I got to give you Montgomery's theorem. So, so he said that when he told Turan, Professor Turan, the Turan hypothesis is false, Turan jokingly responded, so the Riemann hypothesis is false. That is not true, right? The truth of the Turan hypothesis implies the truth of the Riemann hypothesis, but the falsity of the Turan hypothesis does not imply the falsity of the Riemann hypothesis. But Montgomery said Turan had spent so much of his life working on the Riemann hypothesis that his faith was and so great on his thing that it's just a joke that therefore it must be false. So apparently in the last few years of Turan's life, he actually believed the Riemann hypothesis is false and tried to disprove it. Probably because of something like this. But anyway, this is a joke that Montgomery mentioned. But now let me make some comments. I erase this since you have, this is just a little technicality, okay? So I erase this. Okay. So, so Turan looked at the following. It's interesting. I'm doing this lecture because I'm tying up a whole bunch of things that we have done before. Now let us look at this Dirichlet series zeta subscript x of s, or we'll put n of s, whatever. it's approaching 1 as you are going towards the right-hand side. So that means in some half plane, it has no zeros. That's something that we already noticed. Of course, Turan is saying it has no zeros throughout the entire half plane sigma greater than 1, but in some half plane, it is zero free. Okay, so clearly, so here are some remarks. Clearly, zeta ns is not equal to 0 in some half plane. Sigma greater than or equal to sigma n, right? I mean, you look at the inf of all these sigma n's for which it is that. That sigma n, of course, is greater than 1. Right? It's equal in some half plane. So Turan himself showed that that sigma n, Turan showed that sigma n is no more than 1 plus 2 log n over log n. See, this is, you need a function that goes to 1, because as n goes to infinity, zeta ns is approaching zeta s, and zeta s has no zeros to the right of 1. So he is saying now zeta ns has no zeros to the right of 1 plus epsilon. And Turan calculated that epsilon to be no bigger than this. So if you take the half plane, this is your sigma n, right? The Turan sigma n is very close to 1, but here, so he effectively computed this. Now the thing is, Montgomery showed that there exists a C small enough such that zeta ns equal to 0 for some s with sigma in the neighborhood of 1 plus c over log n. I mean, you do get a 0 there for some small enough, log n, right? I mean, I think it's log n or log n. That log n over.
And that's for any n?
Yeah, sorry, log n. So Turan had it with a 2, but he said somewhere here there is a 0. And so consequently, the sigma n is no more than 2 log n over log n, but definitely 1 plus, right? But definitely at least this. So we know the size of this quite accurately in terms of order of magnitude. I mean, sigma minus 1. So this is where things stand right now, at least as far as my knowledge is concerned. This may have been improved subsequently. I mean, as I said, for the last several years I've been working in partitions and Q-series, but I do remember Montgomery excitedly giving a talk in Michigan about the Turan hypothesis and other things. And you know, Michigan was, at that time and even today, one of the real centers for analytic number theory. So this is sort of thing. Now, I won't be here on Monday. So I have a choice for you guys. If you are very conscientious and you want to have class, of course I'd be delighted to hear that. I have very detailed notes of the proof of the functional equation of the Riemann-Zeta function using Hankel's contour. So, how many of you can stop there?
Oh.